All right, so we are going to simplify radicals with different indices today. What we're going to start with is we're going to set up a cubed root. So I want you to write the cubed root of 8. So cubed roots, if you recall from earlier classes, have a little 3 here, and it's the inverse of doing a cube. There's a little bit of terminology that goes with all the pieces here. So the actual root symbol is called a radical. The number inside is called the radicand, R-A-D-I-C-A-N-D. And then this number out here that tells you what root you're doing is called the index. As far as actually doing these, knowing all those pieces doesn't necessarily become a huge deal, but I could see this being knowledgeable questions. And when you have a square root, the index is 2, but they leave that off because square roots are so common. They just kind of dropped the 2 at some point. So know if there's nothing there that that's a square root. If there's a number there, then it changes to something else. So we've learned in the past how to do the cubed root of 8. So let's talk about that now. So the cubed root of 8 basically means we have something that is being cubed, something to the third power that equals 8. What number times itself would be 8? Yes? 2. So this would be 2 here, so that means the cubed root of 8 is 2. Okay, so this is something that we have done before, but it's a little bit interesting. All right, so on the next question, let's look at what if we did the cubed root of 16. Well, if I try to set up a number to the third power that's going to equal 16, there really isn't one. So you could think about it. 2 times 2 times 2 is 8. We just did that. 3 times 3 is 9 times another 3 is 27. It's somewhere between 2 and 3. And if you put it into your calculator, it's going to come out about 2.5. And so I can't really even put 2.5 in here. I'd have to put the approximately equal to sign because it's not actually 2.5. It's something rounded off. So this is not an accurate exact answer. And sometimes we need another way to simplify this to write it so that it is exact, but it's going to match up with all of our other numbers. And so we're going to learn how to simplify things that are a little bit different than square roots. We're going to do cubed roots, fourth roots, etc. I'll teach you the pattern and then you'll know how this goes. So this is sort of your background info, so you can draw a line of some sort to divide that. That's sort of reviewing what we did in the past. Okay, and so what we're going to do now is see how this ties into how we simplified square roots. So I'm going to start with a problem. I'm going to do example number 1. We're going to do the cubed root of 128. And we are going to start just like we would with square roots. So this is a fairly large number. You're going to go down, 8 or 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8. I'll go 9 just for good measure. Because when we do our birthday cake method of prime factorization, we need to have lots of room for lots of layers. So I may not know what goes into 128, but I can tell that it's even. So I'm just going to start by dividing by 2.
64.
And we get 64. And that's also even, so I can divide by 2 and get 32.
16.
By 2, we get 16. Okay, good. You guys got it. And to just keep dividing by 2. And this is one of those strange examples that they're all 2's. And then you're done when you get to 1. So we divided by 2. 1, 2, 3, 4, 5, 6, 7 times. So I'm going to start off by writing out that expanded form for that factorization under a great big radical. So there are 1, 2, 3, 4, 5, 6, 7 2's. So 1, 2, 3, 4, 5, 6, 7. So get that all set up. The only thing that's different from what we did yesterday is with square roots we wanted to look for pairs. If it's cubed roots, we want to think about things that are cubed. So we're going to do groups of 3. So we're going to box 2 times 2 times 2 here, and it's a group of 3 because we're doing cubed roots. And then 2 times 2 times 2. So if you think about it, this is 2 cubed, and that's 2 cubed, and the cube root is the opposite. So what happens then is we can basically, so here's a shortcut to what we were looking at yesterday. There were a lot of steps I wrote out to help you understand it, that essentially if all of these numbers are in a 2, write down a 2. If all of these numbers in this box are 2, write down times 2. Then put your cubed root symbol and put what's left, and then multiply anything you need to multiply. Okay, so we had 2's here. We put that 2 on the outside. They were a group of 3. Since this is a cubed root, that means they all bust out together. They're on the outside. This is a group of 3. They all busted out. The 2's now on the outside. And then we had 1, 2 that was by itself. It's still stuck inside. Okay, so then I can just do 2 times 2, and we get 4 times the cubed root of 2. So this technically means times. There's no times symbol before the radical. But if I were to type into my calculator 4 times the cubed root of 2, I would get the same answer as if I did the cubed root of 128. And I would get the same answer as if I did 2 times the cubed root of, I'm trying to think, 16, I think is what it would be. So we simplify these so that we kind of all come up with the same answers.
Question. How would you put cubed root inside?
So there's a button on there. If you go into the math menu, there is a cubed root function.
Is it the one right
under
here
numbers?
Is it the one right here where it has a little?
We'll talk about that in a little bit, but we're not actually using that button today. So we are not using the button. This is not really a calculator kind of problem, because that will give you a decimal, and we're not using decimals. Okay? So at some point I will show you guys that, but what I want you to focus on today is understanding what this is. All right, so go down and make a number 2. This one's not going to take as much room. We need to conserve some room to do 2 more problems. There's going to be 4, but the first one was definitely the biggest. So we're going to do a 4th root of 81. Okay?
What is that called when it's 4? Like
It's a 4th root. That's just what they call it. Anything past cubed is just 4th root, 5th root, 6th root. They don't have special names. Okay? They just have like a generic way of titling them. All right, so we're going to birthday cake 81. It's not going to take very many spaces. Go down like 4 or 5 spaces.
Can we do 30?
If you're writing small, but you don't want to run into what you're doing up here. So I'm going to have 81. What is a prime number that goes into 81? 3. 3 will go in. And remember, you can check that by adding 8 and 1 together. You get 9. And if the number you get when you add the digits is...
27.
So yeah, and you get 27.
And then 27 is prime.
And then 27 we divide by 3. And we get 9. Take 9 divided by 3. We get 3. 3 divided by 3 is 1. So it's 3's all the way up. So if I'm doing the 4th root of 3 times 3 times 3 times 3, how am I going to group them if it's a 4th root? All 4 of them. So we're going to talk about what happens. If they didn't all group and there was something left over, you would still have the radical. But basically, this answer, so all of these are busting out, your answer is just going to be 3. There is no radical left because all of these are coming out. Does that make sense? If there had been a 2 or another 3 or something left in there, then I would have the 4th root of that number. But if there's nothing left, we get rid of the radical altogether, and you end up with just a regular whole number. So what this means is that 3 to the 4th power is exactly 81, and this one just happened to work out because it's a perfect 4th power.
So whatever power you have, you make groups of that number.
Well, it's called the index, but yes, it's like having a power. It's the inverse of a power. And so since this is 4, we did groups of 4. If it were a 5, you would do groups of 5. If it were 6, you do groups of 6. So that pattern holds for all of them.
So say if 81 was 243, so the last...
Okay, I still have 2 more examples I need to do with variables, and then you can ask me something else when I'm not recording. All right. So let's do number 3. So I'm going to add a new element to 3 and 4. We're going to have some variables, some letters in here. Okay, so we are going to do the cubed root of 64x to the 4th, y to the 6th.
Jesus.
Okay, it is not going to be that bad. It actually works just like the others, except you're going to have a little bit of letters in your answers, so it's okay. So we start with the regular number in front, the 64. We'll birthday cake that. And so we don't have a, actually let's work underneath this one and we'll do number 4 to the right hand side where there's still some room. So if you want to think about, if you want to draw a little dividing line, so you have space for number 4 over there, that would be a good idea.
I was going to say put your birthday cake sideways.
You could put your birthday cake sideways if you wanted. I think it'll be fine. It isn't that many layers. So I'm going to put 64 down here. And a prime number that goes into 64 would be 2. And we get 32. This is looking familiar. 2, we get 16. 2, we get 8. And you're right, it's all 2. So you guys are catching on. So you get 4 divided by 2, you get 2. So don't get really excited and skip over stuff. Make sure you're writing down every layer to the birthday cake. So you're going to have the cubed root. Actually, I'm going to write this underneath so that I have room. So we're going to write this as the cubed root of, and you're going to need a great big sign, and you're going to need to write small. So there's 1, 2, 3, 4, 5, 6 twos. So 1, 2, 3, 4, 5, 6. And then with the x's and y's, we're just going to write them in expanded form. So I'm going to say x times x times x times x. How do I know how many x's to make?
Because of the power.
Because of the power. It's the 4th power, so I'm going to have 4 x's. And then y to the 6th is going to be y, 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 y. Huh? Yeah. All right, so what you do, if this is a cubed root, we're going to do groups of 3, and you do the x's and y's just like you would normal numbers. So I'm going to have...
How many? I know you got 4 x's.
So y to the 6th means that you need 6 y's. Yes. And then we're going to go through and do groups of 3. So I have a group of 3 2's. I have another group of 3 2's. I can do a group of 3 x's and there's 1 x left over. I can do a group of 3 y's and another group of 3 y's. So anything that groups in 3, so really there's just going to be an x left inside. And on the outside, we're going to take each of these. Just hang on. Okay, so when I do the cubed root of 2 cubed, that becomes 2. And then I will have times another 2. And then times...
Y?
Well, let's do this one first.
Oh,
X. And then times y, and you'll have the cubed root of that 1x that was left over. And then we'll just have to simplify what's on the outside. So 2 times 2 is 4, and then I have x, and then y times y is y squared.
I thought you said we couldn't have squares.
So when we're all done, you do. And you won't with your numbers, and we haven't done variables yet, so this is a little different. Okay? So this is what we ended up doing. So we have a group of 2, a group of 2, a group of x's, a group of y's, a group of y's. So for each of these, whatever your group is, you're putting like 1 of those on the outside. Because it's the cubed root of 2 cubed is 2. The cubed root of x cubed is x. The cubed root of y cubed is y. So we went into a little bit more detail yesterday with this, but that's what you will end up with. Okay?
How do you say that? 4x, what, go ahead.
4xy squared and
Cubed root.
cubed root.
Cube root. That's what I was looking for, see if you could say the cube root. Do you think Carol and Steve would like to eat dinner with us at 6:30? Can you text at some point?
Okay,
and let me know
so-
when I make those kind of plans, I can count those numbers?
Yes.
Okay, so look at the 6:30, probably at Olive Garden and this one.
All right, so we're going to do number 4 over here, and I'm going to go back and do a square root with the variables, because we didn't have any variables with our square root yesterday. So you should all be writing this down with number 4. This is our last example before we do practice problems. Okay? So that's 28, x cubed, y to the 4th. And so if this is a square root, they don't put the number here, but that means that the index is 2. So we're doing pairs. We use square roots so much, they dropped the 2 so it would be a little bit less writing. Because we use square roots more than all of the others, and so they dropped the 2 a long time ago and just used the root symbol. If they don't have a number there, you assume it's 2. Okay? So we start with the number. So we're going to birthday cake 28. So I'm just going to do that down here. So 28, you can divide by 7, and that makes it smaller really quickly because 7 is a prime number, and we would get 4. So what prime number goes into 4?
2,
2, and then 2, and we get 1. There's the birthday candle on top of the cake. So then if I'm going to write this out down here so I have room. I have my square root, big old line there. I'm going to have 2 times 2 times 7. And then what do I do with the variables?
x to the times 3, x times x times x.
X times x times x.
Times y times y times y. For those.
Good. And so we know how many x's and y's to put because of those powers. So if this is a square root, that means this is an index of 2. And we're going back to what we did yesterday. You're looking for pairs, only 2 at a time. So we're going to do these 2's
Why
together
is it only 2 at a time?
because it's a square root, which means that the index is 2. Okay, so then we'll do a pair of x's, and then we have a pair of y's, and another pair of
So you have a
y's.
7 and an x left over.
So you have 7 and x left inside. So if you want to write the 7 and the x inside the square root first, you can. What's going to go out here on the outside? Yes.
2 times x times y times y.
2 times x times y, and then we'll clean that up.
It becomes 2x and y squared.
Y squared, and then the square root of 7x. And by the way, we didn't have this in the examples, but if you had an x times x or y times y left over inside, you would also go ahead and make those into powers. You just clean it up
I
at
have
the
a
end.
question.
Yes.
So why'd you get 2 times x times y times
So
y?
2
Wouldn't it just be
X,
4?
y, and y.
Oh, wait, no, you
So
did
no, because you're
y.
square rooting the 4, remember?
Okay.
So we're taking the square root of that. Okay, good questions. We are done.